Okay, hello everyone. My usual first question is, can you hear us? If someone can type something so we know that you can hear us. Can anyone hear us? Please write in the comments. Okay, thank you, Punk and Kara. Okay, so very happy to be on another episode of what we call Stark at Home, where we discuss in a non-formal manner some very deep topics. And in this time, we'll have a very deep topic of understanding how covenants appear on blockchain. We have three of the co-authors of the Collider script paper. So without further ado, and I'll be the moderator. I'm Eli Ben-Sasson, co-founder and CEO at StarkWare. So please introduce yourselves. We'll start, I guess, with Aviv, who's sitting by me.
Hi, everyone. Nice talking and being here. I'm Aviv Levy. I'm StarkWare CPO. I'm working alongside Eli in StarkWare for the past 7 and something years. And before that, spent a lot of time in, Bitcoin and Ethereum, and at the same time doing some vulnerability research. That's about myself.
Ethan, you want to go next?
Sure. I'm Ethan Heilman. I'm a Bitcoin core contributor and cryptographer and software engineer. I'm one of the co-authors on Collider script, and I'm also one of the co-authors on the OpCat BIP improvement. And I've been in the Bitcoin space for a really long time, and very much excited about Bitcoin and the future of Bitcoin, and what capabilities we add next to Bitcoin to help scale it.
Okay, Andrew.
Hey,
and young Andrew Jr.
I am Andrew Poelstra. I am the Director of Research at Blockstream. I've also been in the Bitcoin space for quite a while, mostly working on cryptography kind of stuff. I contributed to confidential transactions, which is not in Bitcoin, but it's in Liquid, it's in Monero, and a few other things, as well as signature stuff. I was a maintainer of the libsecp library for a number of years. Lately, I've been working mostly on simplicity, which is like kind of a wholesale reimagining of Bitcoin script that is decades away, if ever, in Bitcoin. But also been contributing to opcat discussions and opcode research and Bitcoin script and so forth. And I am one of the co-authors of the Collider script paper. This is my son Lazarus here. He will be in and out of frame a little bit. He is not a co-author of the paper. He's just wants to be on the phone. So that's me.
Okay. So I'll say that for me, covenants at Bitcoin are very exciting. I've been in love with Bitcoin since 2013 when I first attended a Bitcoin conference and basically changed my life from academic career to something that is more in crypto related. Okay, what the hell are covenants and why don't they exist today on Bitcoin? So who wants to explain to us, what the hell are covenants?
So I'll go for it.
I'll interrupt you. Sorry. Before one procedural thing, folks, if you have questions, there should be a button for asking questions. So please ask a question. Here's a test question I'll show you, and then you'll see it all. So sorry about that. And after each one of these questions, we'll take questions from the audience. So please, sorry, I interrupted. Ethan, what the hell are covenants and why don't they exist today on Bitcoin?
So the term covenant is a sort of refers to on a legal contract. You can say that future contracts from this contract have to have this clause that comes along with it. And I think back in 2013 and later, people were like, well, we have these Bitcoin outputs and we have these scripts that control the Bitcoin outputs. What if the script could specify that that the spender also has to include some of the original script in the outputs that spend from the original script? So you could sort of encumber an output with additional rules. One of the earliest ideas with this was something called a vault. which makes Bitcoin custody more secure and easier to do, where you can say, if someone spends from this output, I can the new transaction, the new output that's created, I can like sort of spend back to myself, and they have to have, it's almost like a veto on a spend. And so the idea would be that if someone like stole your seed or your secret key and they went to go spend it, they couldn't just spend it to themselves and it would be lost forever. There would be a window of opportunity where you could say, with a separate key, actually, like, I didn't approve that spend back to me. And this would set up a scenario where the attacker and the original holder could go back and forth, with the original holder just like vetoing it every single time they spend it. But this ability to sort of, what's the right way to put this? This ability to sort of encumber future outputs from the current output can also be viewed as the ability of an output which is being spent to inspect the transaction which is spending it. So you could have an output that says, like, whoever spends this output has to spend 1 Bitcoin to this other address here. And so the way that I at least think of covenants today is really more of the output which is being spent can learn details of the transaction that's spending it. And this is typically called transaction introspection. I don't know if I'm too technically detailed there or not technically detailed enough.
Yeah, I mean, let's hear another take on it. Who also wants to go? Not that it wasn't clear, but several different ways of describing something.
Yeah, I mean that's pretty close to how I would describe it, right? A covenant lets you, from a given transaction, control where the coins are going. I guess maybe a short way to describe it is that in Bitcoin without covenants, you have some sort of signature mechanism, and once you sign the input to your transaction, then the coins can just go. Like, it's a binary. Either the coins don't move or they're authorized to go anywhere. And in covenant, you can constrain where exactly they go, basically. Or not even exactly. You can constrain where they go in some way, shape, or form. And that's still a bit of a low-level answer, but I think Ethan actually kind of covered some of the high-level consequences of this, like vaults and rate limiting schemes and delegation and stuff like that.
Yeah. I just want to say that for people that are coming from the non-Bitcoin world, which I guess in this call we have a bunch of those, then it's pretty unclear why it's not the case, because in all of these other spaces where there are smart contracts, then you get by default the smart contract defining that the transactions can do things only if they stand in some other standards, and even then they can only spend money to those standards. So in Bitcoin, that infrastructure, it doesn't work exactly the same way, but this infrastructure of like, okay, you can spend now, how exactly can you spend it? It just doesn't exist today. And covenants is a way to add, like, how do you spend, not just like what do you need to know to spend.
So now I want to ask, like, from a slightly more technical point of view, why don't covenants already exist today on Bitcoin? What is it, like, not to get too technical, but why is it that you cannot assign any sort of restriction to how a Bitcoin is going to be spent further down the line? But first of all, I mean, my image of the world without covenants is that, like, Bitcoin is very much like gold coins or something like that. If I give you a gold coin, then there's no physical way there's no way that I can constrain what you're going to do with that piece of gold, right? It's yours. You go off, you do whatever you want. Whereas if you have a covenant, it means it's a little bit more like a legal contract, or that some of these gold coins can turn into things where there are certain limitations that follow on. You can't use this thing to spend wherever you want. which has good sides and bad sides. But why don't covenants exist today on Bitcoin? Bitcoin is, after all, has a pretty elaborate, computational device that controls transactions. Why can't we just make sure that we can place a covenant on a Bitcoin today?
Yeah. There's two parts to that, right? One is the technical reason, like why can't you do it, and the other is a historical question, like why, how do we get here, right? So the technical reason, as I sort of hinted at, right, is that although Bitcoin has this very elaborate scripting system, all of the opcodes in it, all of the things you can do in script, they're basically pure mathematical functions, deciding a Boolean output, is this okay to spend or is this not? And they're not able to look at the transaction at all, with the one big exception of the checksig opcode. So you got this one opcode that's allowed to check a signature on the transaction. And a digital signature is always tied to the messages being signed. So the signature that you have in your script engine is obviously contains information about the whole transaction, but it's encoded in a way that is designed to allow you to cryptographically verify whether the signature is legit and not do anything else. And kind of a side effect of the underlying math of how the signature is constructed is that you can't just like reach into the signature and directly take data out. Although, as we might get into a bit later, it turns out you actually can kind of do this by abusing the math a bit if we had opcat and stuff. So there's kind of a fun historic question, right? So if we have this elaborate opcode system and covenants are such an obvious and good idea, or just like at least an obvious idea, right? I mean, there are a lot of ideas in early Bitcoin that were just there. How did we get here? And there have been a couple. So let me say first off that in Bitcoin's inception, I'm pretty sure it did have some form of covenant. And there are a couple ideas, and this is even almost deliberate. So in the very early days of Bitcoin, Satoshi had in mind this idea for delegation. And the idea was that you had a script public key, which was encodes kind of what are the conditions under which you can spend. And then you have a script signature, which itself can do further computations. And the idea is that you first execute the script public key. When you're validating a transaction, you first execute the script public key to kind of set the stage. Here are all the keys that are going to be needed. Here's the signature checks that are needed. And then on that stage, you run the scriptsig script. And then that is able to say, well, okay, that public key that you told me, here's like a signature on a different public key, and I'm going to do this. And in fact, rather than doing those original checks, I'm going to do something else. And it turns out this was totally broken, right? So you could take your scriptsig and you could use the op return opcode, which back in the day would return success, and you just stuck this opcode into your scriptsig, and it would override everything in the script pub key and just say the transaction's okay. So anybody could spend any coin by just spending this, right? Totally broken. And this was discovered, I think in 2010. I think in early 2010. Most of this crazy stuff happened there. In 2009, it seemed like nobody really poked at the system. And in 2010, there was this flood of crazy stuff. So, okay, so that delegation scheme was just dropped. So the scriptsig stopped being this kind of arbitrary thing that you could just run arbitrary opcodes on. And op return was changed so that rather than returning true, it would return false and fail the script. So that wasn't really essential to dealing with this bug. And this whole idea of delegation, which is very close to what a covenant is. The idea of delegation is you have a key that you're supposed to sign with, but then later you say, oh, actually it can be this other key. And then if you like add additional conditions, that's a covenant. Or if you only delegate to a different key under certain conditions, that's a covenant, more or less. So, okay, so we dropped this and got a little bit cagey about trying to do these elaborate multi-party ideas. And then the opcodes, kind of even the pure opcodes that existed to do arbitrary computation that might have been used to kind of pull these signatures apart and implement covenants directly somehow. A bunch of those were removed in mid-2010. And the reason for this is that a whole bunch of them turned out to have catastrophic bugs in them. So this includes opcat, which we used to have until 2010. It also includes op substring. It includes multiplication opcodes. It includes shifts and XORs and all these bit operations. It included arbitrary precision arithmetic, which is kind of cool. Something that you'll hear us complain about a lot is that Bitcoin can only work with 32-bit numbers. Well, it didn't used to be that way. It used to be you could do arbitrarily large things, but there were memory exhaustion attacks, so it was just locked down to 32 bits, which even at the time was a bit of a silly thing to do because amounts in Bitcoin are 64 bits. So like surely but it's water under the bridge, right? And then, if I've got my timeline right, it was only after all of this drama that the idea of covenants, as we think of them, appeared. And Ethan might remember the exact. So all of these are Bitcoin talk posts that you can like Google for and hopefully discover. But there's one from Greg Maxwell that I think was called Coin Covenants was the title. And here he's like, oh, wouldn't this be cool if you could do covenants? And then like almost as a joke, he said, let's try to think of like the worst possible thing we can do with covenants. Like, let's think of how like the, FBI could like encumber all the coins and like force you to like say a prayer to George Bush every time you transact and all this stuff. And it's a bit unfortunate that this historically was the community's first introduction to covenants, was this crazy thing. So as a result, we were left with this script system where people were wary of doing cool things with delegation and stuff, where we disabled a whole bunch of opcodes, where we'd only just discovered the idea of covenants, and they were like associated with like crazy cartoonish stuff that we were posting on Bitcoin Talk. And then alongside that, there was some other drama in the Bitcoin community, I think around P2SH and later SegWit, and but we were starting from not a great base to have these things. So in the very early days, we locked down a whole bunch of stuff, and then we were just like ill-positioned. Had we known, if we could look into the future and realize that this is actually an essential and an important thing, I think things would have turned out pretty differently.
Very interesting. First of all, I remind you, if you have questions, please post them using the questions thing. And now maybe the most hotly debated question surrounding covenants: are they good or are they bad? What's your position on that? Like, should they be allowed? Like, suppose there's a magic wand that could introduce them. I mean, later on we'll see that actually such a magic wand already exists today. We're just negotiating the cost. But what are the pros and cons of covenants? Who wants to go first?
So if I could wave a magic wand, I'll probably. Well, I'm not sure it would be my place to add covenants, because if people just start changing Bitcoin with magic wands, maybe the security of Bitcoin is lost. So we might have to protect against the magic wand threat. But assuming that everyone was on board with it, I am very much in favor of covenants. There is this sort of, and Andrew brought it up, this sort of concern with covenants that they're like, okay, this Bitcoin now has a covenant on it, and you can only spend it with these 3 people, and they're all KYC'd or something. And that's why we don't want covenants. But I think that is not a serious risk with covenants. One, because you can basically implement that in Bitcoin today, where you just have like a 2 of 2 multisig, and one of the signers refuses to sign unless it goes to one of 3 addresses. In fact, one of the things that we see a lot in Bitcoin protocol design and things like the Lightning Network is that we use 2 of 2 multisig with another signer that enforces some rule, often some incentive compatible rule, to do things that you would do with covenants if you had them. That essentially Bitcoin has many of the things that you might want to do with covenants. However, they are built on trusting a third party to sign something. And maybe you trust a third party because it's incentive compatible to sign it, like in Lightning. I would lose money if I didn't sign something in a Lightning channel, so I sign it and it's my money anyways, so it's not really like a serious trust issue. But what covenants allow you to do is sort of just remove that from having an online party that has to sign something and just say, hey, this is now enforced in this particular script. So I guess from my perspective, many of the sort of doomsday scenarios that people discuss with covenants, you could build today with multisig, and no one's really building them. And the real value of covenants, or one of the main values of covenants, is taking these protocols that require incentives and parties to be online, and just removing that liveness requirement and removing that incentive requirement and enforcing it at the script level. So speaking for myself personally, I would love to see covenants in Bitcoin. I even had a bet back in 2015 or something, where it was like I would buy anyone a cup of coffee if they could come up with like the worst case covenant scenario, or the dark covenants. And I think Andrew added that he would also buy them a beer if added to my betting pool. And so far, we haven't really heard anything that at least from my personal view, is like an actual threat that we should worry about with covenants.
Ethan, what was the bet exactly? You said that you need to come with something that you can do with covenants that is worse, that you cannot do today, right? Something of that.
I think my bet was like, tell me the worst thing you can do with covenants, like the absolute worst thing. And if you come up with something truly terrible, like I'll buy you a cup of coffee. Because it was at a conference, so just across the street.
There was a condition, right, that you couldn't do it cheaper and easier with multi-sigs. I think was part of the bet, right?
Yeah.
I'll jump in. So,
I wanted to add, like, what? So Andrew, if you could also, like, what's the best thing that could come out of covenants, right? So, like, why should we? What's wrong with the current system? Why do we need it?
So, in my view, the most important thing from covenants would be vaulting, right? And vaults are both a specific idea and a very kind of broad category of ideas. So what a vault is I think Ethan described it. You have some coins, and in order to move those coins anywhere, you first have to kind of declare where you're going to move them, and then move the coins to a staging area for a few hours or days or weeks or whatever you want to do. And then after they've sat in the staging area for the required amount of time, then you can move them to the destination. And meanwhile, if you decide that you don't want to move them after all, or if the person who's moving them is in fact not you, but an attacker who's stolen your keys, then you can unfreeze some backup keys that are in cold storage or whatever, and then you can kind of reset the timer, or you can move the coins back, and there's different variations for what you can do. But essentially, the most common one is that you can reset the timer. So now, if an attacker wants to steal your keys and steal your coins, the best they're going to be able to do is whittle your coins down into mining fees over the course of like thousands of back and forths, where you keep resetting the timer and the attacker keeps resetting it back, kind of thing. And there are other variants with multiple keys where, like, if the attacker has one key but not the other, then in fact they can't even go in circles. Like, you can just claw back the coins. And but in all of them, the worst case is the attacker compromises every single one of your keys and can pretend to be you. Then you just get into this timer reset loop, right? And the attacker is not really incentivized to do this. It takes a long time and they don't get anything out of it, unless they're a miner, in which case maybe they get a little bit of fees from time to time. But like, there are many other ways to artificially convince people to make Bitcoin transactions than to trap them into this weeks or months long doom loop. This ties in closely to the second most important thing, maybe the first, the co-most important thing that you can do with covenants, which is delegation, right? And this, as I hinted, is where you've got a key and you want to say after the fact, like, there's some other key that can sign instead. And so without covenants, you can kind of just do this today with one input, one out transaction, right? So you've got some coins, they're tied to a public key. When you make a one in, one out transaction, you basically replace the public key with somebody else's public key. That's delegation. But in conjunction with covenants, this becomes much more interesting, because now you can say, well, there's a second key and it can be used only under certain conditions. You can say, well, I'm going to delegate to, say, my son's key, but he's only allowed to spend, like 0.1 Bitcoin a day or whatever a reasonable amount of money is these days. I know that that's actually a lot right now. But historically, when I've been having this conversation, that was a very small amount. That's how long it's been. Or I can delegate, like in a business setting, right? You delegate to like different departments and they can spend money, but like they can only spend certain amounts, or they have limits that differ based on whether they're spending within the company or external to the company, or, whatever kind of rules you want. You can assign them two different keys. And then now you have kind of a very elaborate spending policy that can involve multiple participants who are only trusted to the extent they need to be trusted by whatever your business logic is. So those are the two things, and they're kind of tied together in my mind, right? The vault/rate limiting, where like you can't move the coins without a delay, and then there's delegation, where you take all the parameters of vaults and you kind of tie those to different keys.
I think I don't want to get into technical. Like from the high level perspective, I think it had two things that are different sides of what you want to achieve. From one side, you want more people to use Bitcoin, and as much as you can without adding trust in third parties. And you want these mechanisms then to be on chain. You want like smarter money, and Covenant enable you that in some mechanism that Ethan and Andrew explained. And on the other side of things, if you manage to cause a lot of people to join Bitcoin and to hold Bitcoin and to spend Bitcoin and to use Bitcoin, then the other side of things is that you want scale for all those people. So I imagine, I don't know, if you manage to bring onto Bitcoin 1 billion people, now you also want to make sure that they can also use Bitcoin with scale. And at least in my view, covenants give you this as well. So you get like better UX, less trusted third parties, so more people will come. And then on the other side, you get scale to the system. So you can include more people in the system. So that's like why I like it and I support it personally.
So I'll just add my own take that I always say I'm a ZK Stark maxi, and I've been so I think since 2013. I see that someone said here, Simanta is saying, fun fact, Greg Maxwell coin covenants idea that Andrew mentioned earlier was one of the earlier conversation around was inspired by my work on validity proofs, which was called Skip back then in the day. Maybe, I don't know. But so going back, I heard that if you have covenants, you could actually, with a lot of ingenious work done in part by Aviv and Wei King Chen and a bunch of others, there's a way to actually settle a ZK Stark proof onto Bitcoin, which now what it would give you is you would have fully self-custodial Bitcoin style, post-quantum secure, no trusted setup, massive payments at a very low cost, which is like paragraph number 2 from Satoshi's white paper, right? It is, the reason he or she invented Bitcoin was in part because the cost of transactions today on the digital networks is high. Why? Because of manual labor involved in it. And if you want like something that is both fully self-custodial, doesn't rely on manual labor, and allows you cheap transactions, then I don't know of a better way than using covenants and then settling some ZK proof system. And after 5 years of trying out Lightning networks and just practically speaking, you don't yet have the scale and usage. So I think it's something that is worth considering. That would be my own take. So I remind the audience, please, if you have questions, please use the questions tab.
You have some.
We have? Good. No, I have my test question. Good. There's one question. So let's answer. So Adrian is asking, how do you scale covenants? How do you scale with covenants only and no snark verifiers?
I can
L2, something else? Thank you.
I can answer this one. So first, the work that Eli mentioned earlier was mainly Wei King Chen, like it's his work. The thing that is with covenants, you can pre-enforce flow. Doesn't matter which flavor of covenants, but you can pre-enforce that if you want to execute very long function on Bitcoin, you can do that, even if the function execution costs more than the largest transaction that can fit into a block. That's fine because you can take your function and split it into many, many functions, and then you can still execute them by an order, and you can be sure that there is consistency and that there is state transferred between the execution of those functions. So if this function is a Stark or Snark verifier, then you can split it into many, many small pieces, and covenants will enforce the sequential execution using input. It will be very expensive, and you will need to use small scripts, and you will be still limited with what exactly you can do. But you will be able to verify, at least in small script, proof.
Okay. So now we get to the technical meat, and it is. So we thought that there's no ability to do covenants on Bitcoin today, but you guys, alongside Victor Kolobov, the fourth co-author on the ColliderScript paper, amazed the world and shocked us, and basically said, well, you can get covenants today on Bitcoin, but for a hefty price. So now we're just like in the old joke, we're just negotiating the price. We're already established that covenants exist. So who can, how do you get covenants? What is the trick? What is the problem that you're solving in that beautiful paper?
So everyone often when they talk about Bitcoin script, they say that you can't compute arbitrary functions, and this is actually not the case, because you can do things like because there's like an add function and a subtract function and an if function. You can build things like NAND gates, and you can do arbitrary computation on Bitcoin script. But this arbitrary computation can only be done on 32-bit integers, because the add instruction in Bitcoin only works on 32-bit numbers. If you add two numbers together and they become a 33-bit number, well, you can no longer add things to it. It will just cause your transaction to be invalid if you attempt to do an add or subtract to it. So we are actually in this world where we have the ability to compute arbitrary functions on Bitcoin as long as you can fit them within a block. But you can't do this on things like signatures or like pub keys, because you get those in there, and then it's like much bigger than 32 bits. So there's this sort of like world of big script with things like signatures, and this world of, and that's very limited, and then this world of small script, which is very unlimited, but can't do the things that you can't operate on the data you want to operate on. For instance, if you want covenants, you could get covenants, and Andrew did a bunch of really cool work on this, where you can basically take a signature, and if you can do arbitrary computation on it, you can essentially like back out and open the signature to what was signed by the signature, and then look at the transaction which produced that signature, and that would be the spending transaction. But signature is bigger than 32 bits, so you're out of luck. And the trick with ColliderScript is it figures out a way of taking a big script thing like a signature and proving that it is equal to a bunch of 32-bit values. And by doing so, it bridges these two things. It bridges big script into small script. And then once you can prove that this is actually these 10 or 20 32-bit ints are actually the same value as what's in this one big signature, then you can use all of small script's power to extract things from that signature and to do all the stuff that you would want to be able to do in Bitcoin. And so the real trick of ColliderScript is figuring out how to prove that equality by using the hash functions that exist in Bitcoin that are small enough that you can create collisions in them. And then by creating these collisions, prove that two things two different representations are actually representing the same value. I don't know if you want to add to that, Andrew.
Sure, that's essentially it, right? You've got this big script and small script, and in small script you can do arbitrary computations. In big script, you can do check sigs, and if you could do arbitrary computation on the input to the check sig, then you could get covenants. Was the result of some blog post I had, and yeah, if you could somehow bridge big and small script, then that would give you covenants. That would, you take your signature, you'd somehow get it across the bridge, and then you do the computations you need to get covenants out of it. And for a little while in like talks and stuff, I was sort of just like waving my hands and just like rattling off like cat can do this directly because opcat like literally makes you build big things out of small things and vice versa. But really anything that would bridge these things would give you covenants, you know. So if we had arbitrary size arithmetic, you could. If we had, you know, like at one point I kind of casually said if you had SHA-2 collisions, or if you had some sort of hash function collision, then you could do it. And what I was imagining there was something like a large, like a big script object. Like if you could somehow like pre-image it into a small object, then they would be like partners in some cryptographic sense or something. I don't know. I had some very vague ideas here, but all the parts seemed to be there. So I was comfortable just like saying it during talks and stuff. And then Ethan messaged me and said, Andrew, is this true? Like, how do you do it? Like, and then I had to think more carefully about, well, what actually do you need? And it's not quite pre-images, it's collisions and stuff. And then I think entirely independently, Avihu reached out to us and said like, hey, I had the same idea and like I worked it all out and I did it properly. And we were like, whoa, cool. So, okay, we must be on the right track, right? Because we all had the same kind of line of thinking. And then Avihu joined in Victor, of course. And from there, we had the core idea. And we're able to quickly get an outline together. And then I think the majority of work on the paper was optimization almost. Does that match your recollection?
What is this thing with the collider? Like, what are the collisions doing here? Like, what's going on? Like, yeah.
I just want to give just one thing in addition to the story of Andrew is that, so we spoke about it back in May, I think, but then it was like, okay, it was like a very cool idea, but then obviously like writing it is challenging. So then we didn't write it. And then I think a month or two later, somebody asked about this because he was like, well, Andrew keeps saying it, but what does it mean on Twitter? And then Ethan messaged me and said, hey, you know, we had this discussion back then. Do you actually want to write it? So I was like, yeah. And then we were like finding the time, you know, over like the course of a couple of months to meet and do the work of actually writing this. So this is like to complete the story on why it's actually been written.
So what are the collisions they're doing? Like,
well, the thing is like both Ethan and Andrew mentioned is that you can't. There are very limited operations that you can do in big script. So you have a signature, you want to bridge it to the small script list of elements that represent the same signature. But how do you prove they're equal? You can do almost anything on the big script. So one thing you can do is hashing, and you can hash with more than one hash function. So there is a way to recognize that if you took an element and you hash it in a similar way in big script, and then you took a small script element and you get to the same result, because when you hash small script element, they become large script element and you can compare them, then this gives you like a cryptographically assurance that those were the same elements. So yeah, the hard part is that you need to find the collision, and Bitcoin doesn't give you a very easy life with that. Like the smallest collision are in 160-bit hash functions. The nice thing is that if you find a collision, then you can create a bridge. Obviously, it's not straightforward, and the article is like, I think, a 40 pages description of the details. And by the way, it's a very nice one. I recommend everyone at least read the beginning because it has some magical information that I don't know if you will find anywhere else. So I recommend reading it, even if you think that spending $50 million on a covenant is a bit too much. But yeah, that's what you do with collisions. If you work hard and you fight collisions, your reward is this bridge between small script and large script.
So let's see if I understood. So you're saying we would like, if there was a way to copy somehow something from the big script with which you can only verify a hash, but on a big chunk of data, inside to the small script where you could actually run arbitrary computation, then our life would have been really, really great. And unfortunately, I guess Satoshi didn't allow this. So now, like, you can't copy like this string whose hash is on the outside and bring it in. So instead of that, what do you like? How does a collision help you? Like, you compute inside using the Bitcoin script the same hash function that is computed outside.
I can try and give like the picture. I don't want to get into the actual details, but maybe Andrew or Ethan feel like they can. I will just give like in a very intuitive way. If you would have enough, let's say that you have a group of small elements that you feel fine with, that you know to recognize it, right? Then you also know that when you hash them in some way, you get some big script element, right?
Mm-hmm.
So you basically created a group that you can say, well, look, I know this small script element and I can hash them in many different ways, and that gives me a list of big script elements, right?
Mm-hmm.
So now let me find I can get like a big script element being hashed in some way and matches this small script element being hashed in the same way, right?
Mm-hmm.
So I can say, okay, this is, I now know, I can't read big script into small script. So I don't know, when you give me a big script element, I don't know what's written there. Is it 1, 2, 3 or 3, 4, 5? I don't know. But if I manage to take this big script and find his brother that is a result of computation of hashes in the small script board, then I can actually, in the small script board, say, well, the big one was 1, 2, 3 and not 3, 4, 5, because I know I recomputed everything on the small script board and I got the same thing.
Wait, but is the small script world able to refer to the big script world, or not even
No,
that?
that's the problem.
So the trick is, imagine a signature can exist in the small script world, but imagine that you have a value, like a random value, that can exist in both worlds. And you hash that random value. Now, if that random value also collides with the hash of the signature, then you can, since the middle value can exist in both worlds, you can ensure that that same value gets sent to small script, and then you can compute the small script representation of the signature and check if the hashes collide. And if they collide in both worlds, then they're probably the same value. And the argument is that if they are the same value that you've collided, that only requires a single collision. But if they are different, you've now discovered 2 collisions. And that is 3 values that all hash the same thing. And that is significantly more computationally difficult to produce than just a single collision. That is 2 values that hash to the same object. So the idea is that you find this sort of point, you find this object in Bitcoin that, using exactly that object, you get the same value in small script and big script, but in different representations, and then you leverage that to find the collision.
Let me try to describe a much simpler, like, broken kind of system to try to give some intuition for what's going on with the bridge crossing. And I'm not sure I'm going to be any less technical than you two, but it's good to practice this, right?
Could you touch on what kind of information can at all pass on this bridge from, right, like, because if 0 information can pass, then we're toasted, right? So some form of information is allowed to move from the big script world to the small script world, and then you manage to, like, through this, I guess, this needle hole, you put in a whole elephant. So, like, well, what kind of information can pass?
So what information can pass? Well, in big script, you have very few operations. You have checksig, which I mentioned, and you have some hash functions, and you have a couple not super useful opcodes, like interpreting things as booleans and stuff. Let's disregard those. The ones that do anything interesting are checksig and the hash functions. And the hash functions are standard cryptographic hashes. There's SHA-2, there's RIPEMD 160, and there's SHA-1 largest with 3 of those. And as Ethan mentioned, you can do any computation, including those 3 hash functions in small script. So in big script, we have an opcode that will just do it, but it will take a big script input and produce a big script output. In small script, we can do it, but it will take a small script input and produce a small script output. So what
Wait, and what information can pass between the two?
No information. So what information can pass through is kind of this implicit, basically that a value hashes to a particular target is what is able to pass. So actually, there's one thing that I'm missing. I said in big script, you can use these hash opcodes. In small script, you can implement your own hash function. In small script, you can also use the hash opcodes. So here's where the bridge is that you have this op SHA-1 opcode and this op SHA or operate MD160 opcodes and stuff. And those you can put an object from big script into and an object from small script into, and the opcode will work just the same. So the issue, and one more big script opcode that is important is equality checking. So
okay. So you can check the 2 things on the inside and the outside.
You can turn small script element into big script by hashing, and you can do the same hashing in big script, and you can
check that they're equal.
Yes.
Okay, that's important. So you can check equality.
Yeah. You've got some sort of object in big script. We hash it to get a value. You have some sort of object in small script. You hash it to get a value, and then you compare those for equality. And so here's kind of the intuition, right? Here's where the bridge comes from. One second. So the bridge comes from if you could find somehow a big script element and a small script element for which this were true, then that would be your bridge. Like probably just based on, and I say probability, we have a paper and we prove this, but like the intuition is probably because hash functions are really hard to invert and really hard to collide and stuff, then if you could find a pair of elements, one in big script, one in small script, that would be hard to find. You wouldn't be able to find the second one. And like maybe if this is sort of the hypothetical. If SHA-1 was broken enough, then you could find these, but probably it wouldn't be so broken enough that you could find a lot of them, or at least it would be kind of hard to find a lot of them. And then you can use there's lots of techniques to increase the security. If you got a little bit of security, you can always get a lot of security in cryptography. And the intuition is because a hash function is doing it's trying to resist you finding 2 elements in different worlds that hash to the same thing. Then you've got a little bit of security, and then probably you can boost it somehow. So that was sort of the intuition that I had going into this paper. And what we produced, I would say, is a little bit head-bending. Like Ethan was talking about having this middle value that you need to work with, and Avihu was talking about needing to have multiple hash functions that you need to alternate and stuff. And it turns out these are needed to make this work in practice. But the intuition, like the information that's passing, is passing through the output of these hash opcodes and the fact that you can compare their output for equality. Mm-hmm. And then all the rest is just kind of like, once you've got that bridge, all the work is kind of like stringing stuff into the bridge somehow from each side.
Okay, I have a lot of questions, but so I don't see the audience asking, so we'll take the audience's question. If you have questions about this, please ask. There's one question here. Can we just have a trustless bridge from BTC to Ethereum without transforming BTC to a smart contract chain? John Doe is asking.
I mean, the short answer is no. If you had enough infrastructure in Bitcoin script language to create a trustless bridge, that would be enough to get you smart contract can mean a lot of things. I think broadly, people don't want Bitcoin to be able to support these colored coins and all these elaborate DeFi kind of things. And unfortunately, it really seems like that just comes with any addition to script, is you kind of get all these things at once. You get covenants, you get if you could do a bridge. Well, here's a provocative claim I want to make. Being able to do a trustless bridge between Bitcoin and another system, and being able to do covenants, and being able to do DeFi are all the same. Like, if you get one of them, you get them all. That's my personal belief about what's possible to do in script.
Yeah, I would agree with that. I would argue that probably a trustless bridge from Bitcoin to ETH would enable you to build smart contract. Like if you just had a magic opcode that let you do it, you could probably use the bridge to build arbitrary smart contracts in Bitcoin, just because now Bitcoin can reason about Ethereum, and reasoning about Ethereum means reasoning about like smart contracts, which then means that you could write smart contracts in Ethereum that Bitcoin would evaluate the truth of. And so it's like, it's not even could you build it, but the fact that you have it would enable you to build smart contracts in Bitcoin, because Bitcoin would have to be able to reason about Ethereum smart contracts. Maybe there's some loophole that I haven't thought of there, but I think it's like they're almost like definitionally the same thing.
Okay. So we're down to the very last part or question, and those in the audience, if you have questions, please write them now. Okay, there are other ways of getting covenants on Bitcoin other than using Collider script, which is also very expensive, as you read in the paper. What's your favorite way to get covenants? Who wants to go first?
Sure, I'll go first. So my favorite way to get covenants would be opcat, but the reason is that I don't actually care about covenants specifically. So opcat is cool. So it gives you covenants, which is nice, and not in a terribly inefficient way. It's inefficient, it's ridiculous, but it's not as terrible as I first thought. But cat also gets you Merkle structures, so Merkle trees in particular, which then let you do kind of arbitrary computations where for any function that has a reasonably small domain, you can exhaustively list every single one of its inputs and outputs, and then put those in a giant Merkle tree. And then in your script, you use opcat to read the Merkle tree, and then you have that computation, right? Anybody who can verify that you made the lookup table correctly can be assured that you're doing the computation faithfully. And you can do arbitrary stuff this way, right? You can do multiplication in 32-bit fields, which is something you need for Starks, right? But the combination of that and the hash functions are probably you could do the hash of every element in a 31-bit field, right? So you could just basically, you need to have a small enough domain to make this feasible, to make an exhaustive table. But it turns out in cryptography and coding theory and error correction and all sorts of things that you might want to do with Bitcoin, you have these pretty small domains, and then you can do arbitrary computations. So cat gets you that as well. Cat also lets you kind of directly use Merkle trees for what they're kind of meant to be used for, where you could imagine having like a giant multi-sig of I don't know, let's say you're trying to do like 30 of 40 participants or something. You can build a giant lookup table of all 40 choose 30 sets of participants, and then in order to spend the coins, you pick one, reveal the Merkle branch, and you then sign with those keys. And this is less efficient than using something like Frost or Musig that directly gets you this, but what it gets you is non-interactivity, in that every participant can just sign the transaction, and then you take their signature and then put it alongside the proof, and you don't have to go back and forth. And it gives you auditability, which is sometimes an important thing. So you can see exactly which signers signed. So in Frost or Roast, you don't get that, right? You just know that 30 of 40 participants signed, but you don't know which 30. Now, if you ask me which is my favorite mechanism to get covenants, well, that would be transaction introspection, where you directly have opcodes that look up the transaction. So if that was really what I wanted, was just covenants and not this other stuff. Although maybe I could get it. I've never considered trying to go the other direction to abuse a covenant proposal to do arbitrary computations, but there might be a way. But specifically for covenants, I think having the ability to just look at the inputs and outputs of your transaction. So something like CTV, which is limited in a couple ways to prevent some kinds of things. But CTV or TX hash or things in this direction, where you just look at the transaction and manipulate it, would be my way.
Ethan?
I mean, I think so. If I just wanted covenants, and I would go with like a covenant opcode. The most powerful covenant opcode I could find, like TX hash, lets me do everything recursive covenants. But ideally, like Andrew said, I want to do more than just covenants. So like my ideal scenario would be like cat, just because no matter what path you do, the ability to concatenate things together to just join objects is extremely useful. Every programming language has it, or almost every programming language has it. It's just basic functionality. A covenant opcode that allows arbitrary transaction introspection, and then some really nice like big math opcodes to make these to make Bitcoin. You can do addition, you can do multiplication with large values with cat, but it'd be nice not to have to. So like my ideal wish list would be a bunch of different things. Cat surprisingly allows you to do all of these things, but I mean, I don't think we should just stop with cat. And I think probably whatever we do, cat will be useful because it's just such a basic. You have two things and you put them, they become one thing. So I don't know. That's my overly nuanced answer.
Yeah. I have my thoughts are somewhat similar to Andrew and Ethan, in the sense that I think it's very logical to have cryptographic operations in Bitcoin, which means obviously hashes. And to properly use hashes, you have to have concatenation and Merkle trees. And you want hashes also for Merkle trees, and you want hashes for more complex protocol like Starks. So obviously, we need these in Bitcoin to do meaningful things. And then I do want recursive covenants. So I want something that is at least as strong to do that. And cat is one of those options. By the way, I have a unproven claim, but I think it's a nice work to do, which is to basically map each and every serious covenant proposal to be at least recursive and maybe to copycat cat without cat. So this is like because you have already these collider script ideas and you have some maybe other things in your toolbox, it could be interesting to try and take the non-recursive covenants proposals and see if you can get recursive covenant anyways. That's like something that I had in mind. Is a comment to what Ethan and Andrew said.
Okay. By the way, I see here, sorry, a noob question. I've seen some projects that claim they have an ability to scale Bitcoin as an L2 even without opcat, e.g. Botanics. Do you have any insights on what they're doing? And is their solution so much worse than scaling that opcat would unlock?
I'm not familiar with Botanics, but I am familiar with Arc, the covenantless version of Arc, and I would guess that the trade-offs are pretty similar. So and I'm also familiar with some of the hacks that BitVM has done to emulate covenants. Essentially, the way these work, right, is rather than having a covenant where the blockchain is enforcing that coins only move in some particular way, you basically take the lightning trick of having all the participants who care about this doing a multi-signature. And in Lightning, you only have two participants, and then you do this like cool payment path thing to join a bunch of pairwise links. But with Arc, for example, you have a multi-signature of basically all participants in the system, or maybe a threshold number of them or something like that, need to sign off on this. And so to get the full security that you have with covenants, you would need to have like unanimity. You would need every single participant to be signing off on every single transaction, which is obviously impractical. But you can reduce your soundness or your security in reasonable ways, maybe by having a threshold number of participants who are required to sign off on something. But then you've got to reason about that security. In addition, the protocol is much more complicated because you have all this interactivity, and everybody has to agree on the exact transaction structure, and then everybody has to get their signatures in place, and then somebody needs to collect those. And if you fail to have this threshold number of participants, then the system kind of freezes until you do get that threshold. And you need to be able to distinguish between people being offline versus being delayed versus having bad network connections. It's pretty gross, and it's very difficult to scale, right? The thing about covenants is that you can kind of scale to arbitrary number of participants because it's the blockchain itself that's enforcing the rules. versus something like Arc. If you wanted to retain this, like, everybody is personally assured that no transactions happen that are against the rules they want to enforce, then you would need this like increasingly large multi-sig in order to scale up. So yeah, I mean, what is it so much worse was your question? I would say, yeah, it's so much worse.
I would like, I think things like Arc and Botanics are incredibly impressive because they're doing stuff without cat. But as Andrew pointed out, there's like a lot of costs. And all of these schemes would be better with cat. Like, you would just be able to remove trust assumptions and liveness assumptions, and it would be a far simpler protocol. And the other co-author on the cat bit is the CTO of Botanics. So like, Botanics is people at Botanics are interested in cat, and I think understand the value of cat.
Okay, on this happy note, we're gonna end this episode. Thank you all very much for listening in and for the terrific questions. And thank you, Ethan, Andrew, Aviv, first and foremost for your work, co-authored also with Victor Kolobov, Collider Script, which establishes, covenants are already on Bitcoin. We're just negotiating the price. Thank you very much.
All right. Thanks, guys.
Thanks.
Thank you.